Swayam Prabha. Digital India. Educated India.
So let me have your attention. So you see, I will always encourage that you should take a notebook or a piece of paper and make notes. And of course, maybe you are not able to write as fast as I am saying things, okay? But you can at least in shorthand or using keywords note down what I am saying, okay, and then go back and review it, after the lecture is over, okay. Especially I strongly advise you to take all these keywords and go and do a search on the internet, and you will see a lot of nice pictures and a lot of material that you will benefit from, okay. Seeing the same thing being said in different ways helps you to understand that in a more wholesome way, okay. So it's not necessary that you should only stick to one source. Okay, so it is a luxury or wealth that you people have, that we have today, that we can afford because of the internet. Okay, and you can make use of it, and you should make use of it. Of course, for if you want a book to follow, I already told you. Please follow Andrew Presley's book, Elementary Differential Geometry. I told you there is a first edition and there is a second edition, and I would prefer the first edition, which is seemingly more friendlier for an elementary approach. Okay, so let us continue. I was telling you in the last lecture about these ideas of geodesics, okay, and the ideas of geometry, in the situation where you have positive curvature, where you have negative curvature, okay. The usual geometry that we do is geometry for example on the plane, okay, or geometry in 3 space. For that matter, you do geometry in Euclidean space, the curvature is 0, okay. So that is the usual geometry that you do. And when you do geometry, for example, you have trigonometry. For example, you have a triangle, and then you have rules of trigonometry. You have trigonometric functions, and then you have so many nice laws such as law of cosines, law of sines, and so on and so forth. Okay. Now the question is, this is all being done with the curvature being 0. All right. For example, if you are doing it on the plane has curvature 0. All right. Now, if you want to do it on a curved surface, what is it going to be? And the standard models of curved surfaces are one which has constant positive curvature, that is a spherical surface, and one that has constant negative curvature, and that is the so-called pseudosphere. Okay, and then the question is, what happens to geometry? What happens to trigonometry in these situations? That's a question that you ask. So I was last time trying to tell you that, I was trying to tell you last time that this there are these geodesics. Geodesics are paths of shortest distance. All right. Now, and I told you what happens is that if you take for example, plane geometry, okay, then I'm only going to look at surface geometry, okay, and I'm not going to look at higher dimensional geometry, because this course is, being a first course, is only introducing you to curvature of surfaces and in 2 dimensions, and then in 1 dimensions you're going to look at theory curvature of curves. Okay, so we are not going to go to higher dimensional objects. Okay, you can think of a 3-dimensional object sitting inside 4 dimensions, and for the 3-dimensional object you can start writing curvatures. See, for a curve on the plane there is only 1 curvature. Okay, and then if you go to a curve in space, there are 2 curvatures. There's curvature and torsion. Okay, and even if you take a surface, I told you there are 2 types of curvature. One is the mean curvature, the other is the Gaussian curvature. Okay, and then if you this is for a curve in the plane or curve in space or a surface in 3 space, okay. But you can think of an n dimensional object sitting inside an n plus 1 dimensional object, and for the n dimensional object you can write n different curvatures, okay, and study them, okay. This is what is done in higher manifold theory when you want to do it in generality, okay. But we are sticking only to surfaces. So if I am just sticking to surfaces, then I have 3 standard surfaces. One is the plane, and then there is the surface of the sphere, which is positive curvature. Then you have the surface of the pseudosphere, which is the a negative curvature, okay. And what happens in these cases, what happens to geometry in these cases, you see. So that's what I was trying to explain last time, and the reason why I want to do this is I want to tell you about there is something interesting about the Gauss-Bonnet in this situation that links it to geometry and trigonometry, okay. And I want to tell you what is really going on. So you see, so in plane geometry the curvature is 0, okay. In spherical geometry the curvature is positive and we take the curvature as 1, okay. And so here when you say by the way, these are all here I am talking about curvature of a surface, okay. And I told you curvature of a surface, there are two curvatures introduced by Gauss. One is the mean curvature and the other is the Gaussian curvature. And how are these gotten? It so happens that if you pass a curve on the surface, the curve has a curvature vector. Now that curvature vector can be broken into 2 pieces. One is along the normal to the curve, normal to the surface, okay. So one has to be careful that if you draw a normal to a curve in space, you won't get a single normal, okay. There are so many normals, okay. And similarly, if you draw a tangent to a curve in space, then there are many, okay. So normal to a surface is properly defined. So you take if you have a point on a surface, you pass a curve through it, and then for that curve you look at the curvature vector, okay. The curvature vector is from that point directed towards the center of curvature. I told you the center of curvature, that is going to be the center of the circle of curvature, that is going to lie on the osculating plane, and that's a plane which is that plane is determined in a special way, and that in general may be different from the tangent plane to the surface, okay. So the normal curvature vector, the curvature vector can be in some direction in space for a curve in space. You have a question? Yeah. So to recall, you see, the osculating plane is a specially determined plane at every point of the curve, okay. And it changes as the point changes, okay. The plane itself changes in space as the point on the curve changes. What happens is, if you take the simplest case of a curve which is on the plane, okay, then the circle of curvature is on the plane itself. It's the best approximating circle to the curve at that point on the plane. And then of course once you have the circle of curvature, you have the center of curvature, then the radius is the radius of curvature, and we all agreed that the reciprocal of the radius of curvature is the curvature, okay. So for a plane curve, namely a curve in the plane, there is no issue at all. But when the curve is in space, what happens is at every point, you see, you want a circle that is tangent to the curve and and is best fitting. But the point is, if I really think of a circle of a certain radius at a point of a plane of a space curve, I can literally draw that circle in all 360 directions, you see, around. So which circle will you take? Is there a specially determined circle? The fact is that there is a specially determined circle, and that lives on a specially determined plane, and that plane is called the osculating plane, okay. For a plane curve, the osculating plane is literally the plane itself. It's constant, okay. And I told you that 2 things. One is that the rate at which the curve is trying to escape from the oscillating plane, which is measured by the rate of change of the normal to the oscillating plane, is called the torsion. It measures the non-planeness, okay, of the curve. If the torsion is 0, it means it's a plane curve, okay. So torsion, for example, a helix torsion is not 0, okay. For a space curve, you'll always have torsion. Whenever torsion is 0, it has to be a plane curve, all right. That's one thing about the oscillating plane. The other thing is that mathematically you have to show that such an oscillating plane exists, okay? That for every point on the curve, an oscillating plane exists. This has to be mathematically proved, okay? So we will do that, okay? So you see, what I want you to understand is, the picture is that if you are taking a curve on the plane, that at every point you see, depending on how the curve is turning, you are getting a circle of curvature, and that is kind of fluctuating, its size is changing. The only thing is that it is tangent to the curve at that point, but as the point changes, these circles are changing. Their radii are changing, and the reciprocal of the radii also are changing, namely the curvatures are changing, okay? But in 3 dimensions, if you take a curve in space, it's more complicated. What is happening is that there is also a plane that's changing at every point. And that plane, it's only on that plane that the circle of curvature is determined. That's the oscillating plane, okay? So, so you must remember that, you see, if you take a curve in space, then there is an oscillating plane, okay? And that plane contains a circle of curvature, and a radius of that is the radius of curvature. And you can have a curvature vector to be defined from the point on the curve towards the center of curvature if you want, okay? You can take it as a curvature vector. Now all I am saying is that, if you take a surface and take a point and pass a curve on that, this curve is anyway a space curve. Therefore, its curvature vector can be in some direction. In fact, it will be pointing towards the center of curvature for the circle of curvature at that point on the oscillating plane. But at that point, to the surface, there is also a tangent plane, and there is also a normal to the surface, okay? They are in general different. Therefore, you see, this acceleration vector can be broken into 2 pieces. One is normal to the surface, and the other is parallel to the surface. Parallel to the surface means along the tangent to the surface, okay? Basically, what you are doing is you are taking a 3D vector and breaking it down into 2 vectors. One is a 1D vector, which is in the normal direction. The other is a 2D vector, which is in the tangent direction. Remember, the tangent direction is 2-dimensional because it's a 2-dimensional surface. The tangent direction is a plane, okay? So this normal component of the curvature is called the normal curvature, and the tangential component is called the geodesic curvature. And what is the remarkable thing, that as you change these curves on the surface at a given point, these normal curvatures attain a maximum and a minimum. And it was Gauss's ingenuity to given these 2 quantities, take their average. So you can take arithmetic mean and geometric mean. Arithmetic mean is you take the average of these 2 curvatures, and that's called the mean curvature at that point, okay? And then you can take geometric mean, which will amount to taking product of those 2 curvatures and taking a square root, but you don't want to have this square root always messing around. So you get rid of the square root and just take the product of the curvatures. And that's what is called the Gaussian curvature. So whenever you talk about curvature of a surface, you are only talking about Gaussian curvature or mean curvature. And I am in particular only interested in the Gaussian curvature in all these cases. So if you take the plane, you see the Gaussian curvature is 0, okay? Because you draw any curve on the plane, you see at any point the curvature vector will be pointing along the plane. So and the normal to the plane will not have any component of this curvature vector. Therefore, for a curve on the plane, the normal curvature is 0, and the curvature is equal to the geodesic curvature, okay? So the Gaussian curvature therefore is 0, okay? If you take the sphere, what happens is that, at every point, if I take a point on the sphere and I want to get the Gaussian curvature, what I have to do is I have to find maximum and minimum, curvatures, normal curvatures. You see, a sphere is curved the same way in all directions. So essentially what's going to happen is that you are only going to get one value, and you are going to get square of that. The maximum normal curvature and minimum normal curvature, they will both be the same. They will both be equal to 1 by r numerically, where r is the radius of the sphere. And if the radius of the sphere is 1, they are both going to be equal to 1. The product is going to be equal to 1, okay? So therefore what happens is, if you take the case of spherical geometry, okay, if you take a unit sphere as a model, then the curvature is actually 1. It's always positive. It's constant positive, okay? Again, I should tell you that there is a converse also. If there is a surface, nice closed surface, smooth surface, such that the curvature is, constant positive, okay, then, you can show that it has to be a it has to be a sphere. Okay, and in the case of sphere, maybe you may also have to look at the other thing, namely if you find the mean curvature, that is also 1. Okay, because again the maximum and minimum are both 1. Okay, so if you calculate that, you will see that but let us not worry about mean curvature at the moment. Okay, let us only worry about Gaussian curvature for surfaces. Okay, so and what happens in the case of hyperbolic geometry? I told you in the case of hyperbolic geometry, you have to look at the pseudosphere. Okay, and the pseudosphere is the is something like this, like something like a trumpet. Okay, surface of a trumpet, if you want. And the point is that this is negative curvature, because at any point what happens is that you get a saddle, namely you have the circle of curvature in one direction is pointing in one direction, has its center in one direction, and whereas in the other direction the circle of curvature has the center pointing in the other direction. Okay, therefore moral of the story is basically you are having a maximum in one direction, a minimum in another direction, and this kind of thing is what is called a saddle. Okay, which you have studied for example in multivariable calculus. So every point is a saddle point, and saddle points are exactly points of negative curvature. Okay, and standard example is if you take a torus, all the points in the outer bulging thing are all positive curvature. Okay, and all the points in the inner part which is curved like this, okay, the inner part, you can see at every point you have one curve like this, you have the other curve in the other direction. Okay, and you can see that the product of curvatures will be negative. So that's negative curvature, the inner side of the inner part of the torus. Okay, and the outer bulging part has positive curvature. Okay. Of course, it's another matter that the total curvature is 0. Okay, that's because of the Euler characteristic and Gauss-Bonnet, as I told you. But anyway, the point is that you can take this hyperbolic geometry model, which is so this is what is called the pseudosphere. Okay, and this has negative curvature. Okay, and you can make that negative curvature as -1. Okay, now the question is, these give you 3 types of geometries. One is plane geometry with 0 curvature, then you have spherical geometry with constant positive curvature, and you have hyperbolic geometry with constant negative curvature. The question is, what happens to whatever you know in ordinary geometry, namely when the curvature is 0, what happens to that in the positive curvature case and the negative curvature case? Okay, you want to study that, and there are interesting things that happen. The first thing is, as I told you, the motivation was to look at this simplest result that we always study in school, which is that the sum of 3 angles of a triangle is 180 degrees or pi radians, right? That's the simplest result that you learn all the time. Okay, now it's based on the fact that the angle around a point is 360 degrees, and the angle across a line on one side is always 180 degrees, right? It's only based on that. Now the question is, what happens to this, for example, this theorem, if you go to spherical geometry, what happens to this theorem if you go to hyperbolic geometry? Okay, there's something interesting happening, and whatever that interesting thing is actually, if you start making it very, very concrete, it leads to what is called the Gauss-Bonnet theorem for curves on surfaces. Okay, so I want to explain that because it's very, very interesting. So the first thing is, we need to use the ideas of geodesics. Okay, now why do you need to use the idea of geodesics? Why should you look at geodesics? That's a good question. I've already told you geodesics are important because I want shortest path. And for example, assume that you are in some mountainous terrain or unknown terrain, let us say, and you are to navigate from one point to another point. Okay, then how do I know if it's an unknown terrain? How do I know that this is the shortest path? Okay, so what I would do is, suppose I have to only travel by road. That means I have to travel along the surface. And that is what going along the surface is called the geodesic direction, and the complementary thing to that is a normal to the surface. Okay, so in the geodesic direction, that means along the surface, if I want to travel, what is the shortest path? So what you can imagine is that, suppose you are like in a sci-fi movie, you have landed on another planet and there is a terrain, and then there are 2 teams that are landing on 2, let us say, different parts of the planet, and then in the middle there is some big curvy mountainous terrain, and then both of them have, one of them has to meet the other, then you have to travel. And then the question is, what is the had it been a perfect sphere, then it's very easy. You could have just taken the the large circle passing through these 2 points and taken the smaller arc. Okay, that's the obvious choice. But suppose it's a kind of wavy mountainous terrain. Okay, then the question is, how will you do it? What you would most likely do is you send something like a drone that will take a photograph of the surface. Okay, and then now use your knowledge of differential geometry to take the surface profile, okay, the terrain, and then start trying to compute geodesics between these 2 points, and then map out a geodesic. Okay, and all this sounds very hi-fi, okay, but actually it's in principle doable with enough computing power and with and all the required mathematics, all the formulas are available. You can really do that. Okay, so you can understand this is very, very important. Okay, but then at least in our point of view, let us approach it from a very, very simple thing. See, we want to look at this result. This is at the school level. I don't know whether you want to say elementary school or whatever it is. If you draw a triangle, okay, like any triangle for that matter, then you have angle A, the sum of the angles is 180 degrees, and this is also pi radians. Okay, so this is a very, very fundamental result. This happens for a triangle on a plane. All right. Now the question is, what happens to this kind of result if it's not a plane? Okay, so in general, if you draw a triangle on a surface, what happens? Okay, now but then let's break it down into 2 levels of difficulty. Okay, let's first try to see what do you mean by drawing a triangle on a surface. At least let us look at the 2 standard cases of surfaces with constant curvature, namely constant positive curvature is spherical geometry, it is the case of a sphere. Okay, and constant negative curvature is the case of a pseudosphere. Okay, what will you do there? All right, so notice that so you see, so look at what is happening with the case of a triangle. You see how do you get this triangle? See, what you have done is you have taken 3 non-collinear points, okay, and you have joined them by straight line segments. Now look at it from a differential geometry viewpoint. Okay, what are those straight line segments? Aren't they geodesics? They are the shortest paths. Okay, so what you have done is you have taken 3 points and you have joined them by geodesics. All right, and you have got a geodesic triangle. Okay, now this tells you what has to be done on the sphere. So what will you do on the sphere? It's very, very simple. On the sphere, what you will do is you will take 3 points. Okay, and you see, if I really in the plane, if I really want a triangle, what should I do? I should take 3 points which are not collinear. If they are on the same line, what does it mean? They are already on the same geodesic. Okay, they should not lie on the same geodesic. Okay, so on the sphere, basically take 3 points which don't lie on the same geodesic if you want. All right, but that's not an important thing. The point is you take 3 points, and then what you do is you want to draw a triangle on the surface of the sphere. But now remember, you cannot draw straight lines. What will you draw? Of course, between 2 points I can draw so many curves. The point is draw the curve of least distance. So draw the geodesics, the shorter geodesics. Okay, so for 2 points on the sphere, there is a great circle, there is a unique great circle passing through that circle of largest radius. It will be having the center the same as center of the sphere. It will be a plane section of the sphere through a plane passing through the center and containing those 2 points. Okay, and these 2 points will have on the great circle will have a minor arc and they will have a major arc. You take the minor arc. Okay, if you want shortest distance. All right, so if I draw it, you see I will get, my picture will be like this. Okay, my picture will be like this. So I will have this is on the sphere, I will have A, B and C. All right, and the thing is that these are all great circles. And why great circles? Because these are the geodesics on the sphere. Okay, so that is what is going to happen uh, when you know, so this is what is meant by drawing a triangle on a sphere. Okay, now what you can do is, what is the sum of the three angles? Okay, now again there's a little bit of thought. When you have two lines and you have a point, then an angle is uniquely determined, but now you have two curves at a point. But then calculus tells you how to define the angle between two curves at a point. What you do is you take the tangents of those two curves at that point and take the angle between the curves. So you see, calculus gives you a way of even, if two curves pass through a point, what do you mean by the angle of intersection at the point of intersection? Basically, you have to take the tangent directions to the two curves at that point, and these are now two lines, two straight lines, and you take the angle between them. So basically what I am going to do is that, you see, for example, if I take the point A, then I draw a tangent direction like this, and I draw another tangent direction like this, and this is my angle A. Okay. Then if I take the point B here, I draw one tangent direction like this, I draw the other tangent direction like this, and this is angle B. Okay. And then at C, I do the same thing. I draw the tangent directions, take this angle, and this is angle C. Okay. So now the question is, what is angle A plus angle B plus angle C? What is it going to be? Okay. So in the case of the plane, we got 180 degrees or pi radians. The question is, what is it going to be in the case of a sphere, for a spherical triangle? Okay. It's obvious if you look at the picture that this is going to be certainly greater than 180 degrees. It's going to be certainly greater than pi. Okay. For example, I can do the following thing. Just imagine this. I can start on the surface of the earth. I can start at a point on the equator, go all the way up north. Okay. Then I can go down perpendicularly along the quadrant and then come back. Then what happens is I get a triangle, spherical triangle, with all three angles 90 degrees. Okay. Therefore, the sum of the three angles is 200 and it's 270. So you see, if I draw something like this, I'm just saying that if suppose this is the North Pole, this is a hemisphere, okay, and then this is the equator, okay, and here is and I can take one like this, and I can make this 90, okay, and I can make this also 90, and this will also be 90, okay. So sum of the three angles will now be 270 degrees, okay. So it's certainly greater than 180, okay. So you can see that the sum of the three angles of a spherical triangle is greater than 180. That's obvious. And why is this happening? Intuitively you will say, well, because it's bulged, right? It has bulged, the surface is bulged out. That allows the curves to widen at the vertices. Okay, the angle can be made larger, and therefore you are getting this. Okay, well, that's a qualitative question. Answer. But as far as mathematics is concerned, you have to quantify it. What is the quantification? So the question is, what is this? Why is this difference happening? Why is it greater than 180? And if you believe that it is greater than 180, which it is, what is this difference? What is the significance of this difference? You can see that the significance of that difference is, the difference is happening due to curvature, all right, and therefore this difference has also got to do with curvature. Okay, so here is the very beautiful thing. The beautiful thing is that if you calculate angle A, so here is the result. The result is, if you calculate angle A plus angle B plus angle C and take away 180 degrees, okay, this is a positive quantity, and guess what it is? It is actually the total curvature. It is the total curvature of the sphere restricted to the area of the triangle. Okay, okay. So the sum of these three angles, okay, this actually turns out to be total curvature, Gaussian curvature. So of the triangle ABC. Okay, and what is the total Gaussian curvature of the triangle? What does it mean? What does total curvature mean? That means you have to take curvature function at every point and you have to integrate it over the triangle. And you see, you are integrating over the triangle, which is a curved surface. So it's a curved surface area, it's a curved surface integral. Okay. and then but you are integrating you are integrating the Gaussian curvature. Gaussian curvature is constant, okay, and if you take the unit sphere, the Gaussian curvature is 1, okay, it's plus 1. So you are integrating plus 1 over the curved surface of the triangle, but that's just integrating the integrating 1 over anything will give you the measure of that, okay. If you integrate 1 over an arc, you will get the arc length. If you integrate 1 over a surface area, you will get the surface area. If you integrate the function 1 over a volume, you will get the volume, okay. Basically, integral dx is going to give you x, the variation in x. Integral ds or d sigma is going to give you the total area. Integral dv is going to give you the total volume, okay. Therefore, you have to get, you should, essentially what will this be? The total Gaussian curvature will be just the area. So this is just exactly equal to for curvature, for Gaussian curvature is equal to 1. This is going to be the area of the triangle ABC. So you see this. So here is the interesting thing. The difference between, the sum of the 3 angles of a spherical triangle and 180, the excess, is exactly the area of that spherical triangle, the curved surface area. So here, of course, let me write it as curved surface. And here again you are seeing something. The difference is to the total curvature, okay. I told you that this is the kind of result you get in the Gauss-Bonnet for surfaces. For a closed surface, I told you the total Gaussian curvature is 2 pi times the Euler characteristic, okay. That is also a statement about the total Gaussian curvature, right. And here also you are saying that the total Gaussian curvature is this difference, the difference between the sum of 3 angles of a spherical triangle, geodesic triangle, okay, a difference of that from pi. That's exactly the area. So you have a question. Yeah. So this the point is that you are what you are worried about is that So it is a good question to ask that the left side is sum of angles, sum of the 3 angles minus pi, which is also an angle. It's like an angular measure. On the right side, you are getting total curvature, okay, and that is over an area. So for the moment, if you take curvature as 1, then you are getting the area. So it seems to be dimensionally wrong in some sense, but you should not think of it like that. So it's not about dimensions. Here it is a you can see this as a fact probably by also looking at the idea of what is called a solid angle, okay. So there is a way of making sense of the solid angle subtended at a point by a portion of a surface, okay, and then using the solid angle also you can make sense of it. But then again, you should, I mean, if you think like that, probably there isn't any explanation that I can think of, okay. Probably later on I will see whether I can say something in connection with solid angles. But the point I want to make is that you are integrating curvature over an area. So it's basically curvature is a numerical function, okay, and you are integrating it over area. So the dimensions of this, if you integrate a function over an area, for that matter, if you integrate a physical quantity over a region, you are only adding that physical quantity at every point of the region. So if the physical quantity has a let us say dimension, then the result will also have the same dimension. Therefore, if you add the curvature at every point over a region, the total curvature should also have the dimensions of curvature, and you can make sense of curvature as an angle, okay. So there is even for the case of a circle, the radius of the circle, if you add the curvature over an arc, okay, over the arc length, all right, then you will get suppose the arc length is S, okay, and the radius of circle is R, okay, then if over this S, if you want to add, so if the radius of circle is R, the curvature is 1 by R, and you are adding 1 by R over this arc length S. So you are but 1 by R is a constant function, so it will only return S by R, but S by R is theta, which you see is an angle. Therefore, you can see that in this sense, curvature has dimensions of an angle. Okay, so you can reconcile it like that. Perhaps that's the only explanation I can think of at the moment. Okay, if you have a different radius, of course, you can see that the area will get magnified, and then you will get that also into the picture. Yeah, you will get something like that. In fact, yeah, I mean, there is also an interpretation in terms of solid angle, okay, which we will come to later on, okay, and this will, when we study Gaussian curvature, we will come to that, okay. But I am just trying to convince you that if you at least look at ordinary curvature over a curve, you should get the angle, okay. And in fact, since you asked this, I should tell you that this if you take, for example, if you recall the Hopf's Umlauf science, what does it say if you take a simple closed curve, a nice smooth curve on the plane, and then you start looking at the tangent direction as it goes around once, okay, and measure the tangent angle at every point with respect to, let us say, positive x-axis or some fixed direction, and then add all of that, you will get only plus or minus 2 pi, okay. But then you can make sense of this this whole integral as integral over curvature. So actually, that is the simplest case of Gauss-Bonnet, where you are actually getting that the total curvature is an angle, and it is, for this case, plus or minus 2 pi, okay. So in that sense, curvature, you can say, has dimensions of, has angular dimensions, okay. So I think that's a reasonable way to think of it, okay. I will, of course, later on tell you if I can, when I think I will do that. Later on, I will relate it to, solid angles and things like that. And there, I think you will get the analogs for, solid angles subtended by an area, curved area, okay. So there also you will see this analogy, okay. Okay, so this is another interesting question. So, see, in ordinary geometry, okay, so this is very interesting. See, in ordinary geometry, suppose two triangles have the same set of angles, then they will be similar, right? That is the so-called AAA criterion for similarity, or AA criterion for similarity, because two angles are enough. The third one is determined because sum is 180, okay, degrees. So if two triangles have similar angles, I mean have the corresponding angles equal, then they are similar, and conversely, okay. Now something interesting happens in spherical geometry. If two spherical triangles have, if they are similar, that means if they have the same angles, then they will be congruent, okay. So that's an amazing thing that happens, okay. And the fact is that the the sine law in the usual case of triangles tells you, that the sines of the angles are proportional to the opposite sides of the angles, okay. It says the opposite sides are determined only up to a ratio given the sines of the angles, but we will see in circular geometry, spherical geometry, okay, that actually the angles determine the sides. That is the reason, if two spherical triangles are similar, that means they have the same corresponding angles, then they have to be congruent. That means even the sides, the curved sides, the arc lengths have to be equal, okay. So this is a beautiful feature of spherical geometry, which is very different from, ordinary geometry, and we will see it, okay. So this is what makes, spherical trigonometry very interesting, okay. So yeah, so let me get back. Now similarly, so this is the, this is the case of spherical geometry, okay. So the fact that, the sum of three angles of a triangle is 180 degrees on the plane, On the sphere, what happens is if you take a spherical triangle, the sum of three angles exceeds 180, exceeds pi numerically by the area of the spherical triangle. Okay. Now, in the plane also you see this, so let me write this here. This is a version of Gauss-Bonnet for spherical triangles. Okay, so let me write it like this. Okay. Now, is there a similar? Is this also a statement in the plane? You can ask, and that is correct, because on the plane, what is happening? If you calculate A plus angle B plus angle C minus pi, what will you get? You will get 0. Okay, and that is the total curvature of a triangle, because the curvature I am measuring, the curvature is 0. The Gaussian curvature is 0. You are on the plane. Therefore, if you take a plane triangle also, the sum of the three angles of the plane triangle minus pi is actually the total Gaussian curvature of the triangle, which is 0. So it is the same, So here is a beautiful thing. This simple thing that sum of the three angles of a triangle, on the plane is pi, is actually the simplest, is one simplest avatar of Gauss-Bonnet. Okay, that's what I want you to understand. That it is pi just says that the difference is 0, and that 0 is actually the zero Gaussian curvature. Okay, that shows up for the surface of a sphere. Okay, now what you can do is you can imagine now you can do the same thing for, this is for spherical geometry. Try to do it for hyperbolic geometry. So what happens to the situation of hyperbolic geometry? So so I told you in the case of hyperbolic geometry, you can take the model to be the unit disk. Okay, and the way hyperbolic geometry, one way to think of hyperbolic geometry is that you have this unit disk, and so I'll just here is my plane here, and this is the unit disk on the plane. Okay, and what is actually happening is that there is a hyperboloid. Okay, there is a hyperboloid, and so something like this. Okay, and basically what you are doing is that you are projecting it onto the unit disk, and everything is happening, whatever is happening on the hyperboloid surface, that is being seen on the disk. Okay, and I told you that in this case what happens, see in the unit disk, I told you it's very interesting. What are the geodesics? I told you the geodesics, if you take 2 points on the unit disk, then the geodesic is a unique circular arc passing through those 2 points, with the circle being orthogonal to the unit circle. So basically what is going to happen is that if I take 3 points like this, and now I want to do the hyperbolic geometry version of sum of three angles of a triangle is 180 degrees. Okay, so I have to draw a hyperbolic geodesic triangle. That means I have to take 3 points in hyperbolic space. Okay, and I have to draw 3 geodesics, hyperbolic geodesics, and then I have to write calculate the sum of the 3 angles of a triangle. Okay, so what is the geodesic? I told you for let's say for this point B and for the point C, what I have to do is I am supposed to draw a circular arc like this with the property that it passes through B and C, and you see it should be normal to the unit circle. So here it has to be normal, here also it has to be normal. Okay, so this is the geodesic. And as I told you, it's very interesting that this distance is lesser than the straight line segment distance, and that's because of the hyperbolic metric. That is because of the negative curvature. You seem to be if you normally look at it, it looks like you're traveling more, but actually you're traveling lesser distance. And I also told you that if you took the center of the unit disk and then you take a point P, and as this point P moves to the boundary, the hyperbolic distance goes to infinity. Okay, so it's a very different kind of distance as you perceive from the one that you perceive normally. Okay, so anyway, so you see, now you can imagine what I'm going to do. I am going to similarly draw I want a hyperbolic geodesic triangle. So what I will do is I'll again draw one more, I will draw another circle like this, and this circle again passes through A and B, and here it's normal to the unit circle. So here also it is 90 degrees. So, and I will get this one, and then similarly I will get one more here. Okay. So, you see your hyperbolic triangle now looks like a a kind of pinched a triangle whose sides have curved inward. Okay. Whereas in contrast to a a spherical triangle where they have bulged outward, and this curving inward is exactly a sign of the negative curvature. Okay. Now again, what is the sum of the three angles of a triangle? Again, making sense of the three angles of a triangle is not a big deal, because I take this tangent, I take this tangent, this is angle A. Okay. Similarly, I take this tangent, I take this tangent, this is angle B. Okay. And then I take this tangent here, and I take this tangent here, and this is angle C. Okay. And now you can, it's obvious from the picture that the sum of the three angles of the triangle is less than 180 degrees. Okay. So what is the difference? Okay. It is going to give you again the total curvature. Okay. And if you are going to take the curvature as, mind you, this is negative curvature, that's why you get a negative number. Okay. So you will get negative, if you take the curvature as 1, you will get negative of the area of that triangle. Okay. So angle A plus angle B plus angle C minus pi, this is going to be a negative quantity, and this is going to be total curvature, total Gaussian curvature, curvature of the triangle ABC, and this is going to be if Gaussian curvature is taken is -1. Okay. So it's going to be -1 into area of a triangle ABC. Okay. So the minus is to tell you that A plus B plus C is less than, sum of the angles is less than pi. Okay. By what amount it is less than is actually, interestingly, up to a sign, it is again only the area of the geodesic triangle. Okay. So you see, this is again nothing but this is again Gauss-Bonnet for hyperbolic triangles, hyperbolic geodesic triangles. Okay. So you have these three cases. Yeah. So the point I want to say is that so for example, so let me explain this just in case some of you have not got it. So you see, how do I get this? I'm trying to draw a geodesic triangle. I have to take 3 points, and I have to take pairwise these points and join them by geodesics. Okay. So what is the, for example, if I want to draw this edge from A to C, okay, what is this curved edge? What is it? So the question is, it's supposed to be a geodesic for the hyperbolic metric. Now the geodesic for the hyperbolic metric, how is it defined? It is arc of the circle passing through those 2 points, and the circle has to be orthogonal to the unit circle. So that means what I do is I draw a circle like this. Okay, and the circle passes through these 2 points A and C, and it is orthogonal to the unit circle. So therefore, at this end, it has to hit the circle at 90 degrees. Here also, it has to hit at 90 degrees. Okay, and you have to take, there's only one such circle. You have to take that particular circle and look at the arc through that circle, or lying on that circle from the point A to the point C. So in this way, you have to draw the geodesics, and you join all the 3 points by geodesics, you get this geodesic triangle. Okay, is that fine? That's fine, right? So all right, so this is Gauss-Bonnet. Now this is whatever I have said. So you see, the import of the story is the sum of 3 angles of a triangle is the difference with pi, which is 180 degrees, pi in radians, that difference is actually reflecting the curvature. Okay, and if you make the curvature as 1, that is exactly the up to sign is just the area of the triangle. Okay. And now this is one level of let us say complication if you want. Let me have one more level of complication. So what I can do is I can do the following thing. See, I can on the plane, what I can do is, why draw a triangle? Why not draw a curved triangle on the plane? Okay, so what I can do is on the plane itself, I can take 3 points A, B and C. Okay, and I can draw a curved triangle. So a curvilinear triangle is basically a triangle that is gotten by, you join the 3 points by curves. Of course, if I join them by straight lines, basically I am joining them by geodesics. Okay, so the question is, I can do this. All right, and again I can still ask for what is angle A plus angle B plus angle C minus pi if you want. All right, so I can do that. So you see, if I draw something like this, so again it's not a big deal to make sense of the angles, because after all you can draw tangents to the curves. So this is angle A, and then here this is angle B. Okay, and this you draw tangents here, this is angle C. Okay, the question is again, what is angle A plus angle B plus angle C minus pi? What is this? Okay, of course, because everything is curved, you don't expect it to be 0 or whatever. It can be positive or it can be negative, but you can see one thing for sure. Whatever it is, it has got to do with how these curves are curving. You see, it has certainly got to do with how the curves are curving. You may say, well, it's got to do only with how the curve is curving at these 3 points, but somehow it's very interesting that it's even got to do with how eventually how a curve curves at a point has got to do with how it's been curving all along. Okay, this is a very qualitative statement, but it can be mathematically quantified. Okay, so guess what you should expect is that this should also be total curvature. I mean, if you believe Gauss-Bonnet mathematics is that if something happens in a special case, if it's nice, it should simply happen all the time. Okay, so this should also be total curvature, and guess what, it is total curvature. Okay, this is actually the total curvature of all, you add the curvatures of all those 3 curves along the curves. That means what you have to do is, at every point of the curve you take the curvature function. Mind you, the curvature is going to be what? It's going to be only geodesic curvature, because it's a plane curve, there is no normal curvature. So you take the geodesic curvature, and that changes at every point of the curve. You add all the curvatures. Okay, that means you have to integrate curvature over every arc. Okay, every curved side of the triangle. Add it, and lo and behold, that is exactly this quantity. So the fact is that this is equal to, okay, actually is equal to again total curvature. Okay, and here of course the curvature is actually the geodesic curvature, and because you are adding something, mind you, let me just add a small technical thing, that when you are just thinking of curvature, you are only taking reciprocal of the radius of curvature, but I am not, I also have to keep track of whether this is the curve is going this way or that way. Okay, therefore what you have to do is you have to put a sign to the curvature, and it's called signed curvature. Basically what you are trying to do is you are trying to measure curvature as a vector. So what happens is that the vector should point towards the center of curvature from the given point. And mind you, the point is that you are adding a vector quantity, not just the scalar quantity. Okay, so for example, if I can manage at all the 3 points, the angles are 0, then this difference is going to be minus pi. So I'll get a total negative curvature. Okay, and if you are going to only integrate curvature thinking of it as a non-negative function, only the magnitude of the curvature, you will never get a negative sign. So you must be careful that you have to introduce a sign to the curvature. So basically you have to think of curvature as a vector. Okay. So if you do it like that, this is also the total curvature, and this is Gauss-Bonnet. Okay. So this is Gauss-Bonnet again. This is again Gauss-Bonnet. Okay. Now this is on the plane. Again do it on the sphere. Okay. So what happens on the sphere? Okay. What happens? So I take again the sphere. Okay. I take 3 points. Okay. And of course, there is a geodesic triangle. Okay. There is a geodesic triangle whose edges are arcs of great circles. And if I add, I know if I take angle A plus angle B plus angle C minus pi, I will get the area of the triangle. That's something that we have already seen. That's provided all these three are arcs of large circles. But again, I can play the same game. Why draw these? I can just draw any curves, nice smooth curves on the surface of the sphere. So what I can do is that I can draw something like this. So let me draw something. After all, I can do whatever I want. So I will do this. So here's my triangle. Now this is a highly non-geodesic triangle. Okay. And this is again, so again these are A, B and C. And again, I can make sense of what is angle A plus angle B plus angle C minus, minus pi. What is this? Okay. Again, you don't know. It can be positive, it can be negative. You really don't know. All right. So the question is, what is it? Again, it is total curvature. Okay. Again, it is total curvature. But there is a small interesting thing. When you are talking about now, so you see, the region that I am talking about is this region. This is this, this is this curvilinear triangle on the sphere, okay, on the surface of the sphere. What is happening is there are now two types of curvatures involved. Okay, there is the bulged region, the area, the interior of the triangle, which is the curved surface. There, what is coming into play is the Gaussian curvature. Okay, and on the boundaries are also matter. The boundary curves also matter, because they are the ones that you let to be free. You are not restricting them to be geodesics. What happens to the boundary curves? The boundary curves also have curvature. The boundary curves will have both at each point of the. So if you take a point of a curve on a surface, I told you that the normal part of the curvature that goes to the contributing to the curvature of the surface. Then I told you there is a geodesic part. Okay. Now that geodesic part is what is going to tell you what is happening to the curvature along the surface, along the tangent to the surface. And guess what? What is going to happen here is that this is again total curvature. Okay. And now the curvature will have two contributions. You will have one contribution due to the surface inside, the surface of the triangle. That contribution will be the total Gaussian curvature. Plus, on the boundary curves, you will have a contribution. On the boundary curves, the contribution will be due to the geodesic curvature. Again added, this is equal to A plus B plus C minus pi. Okay, so that is Gauss-Bonnet. So this is this will be. So let me write this down: Gaussian curvature, total Gaussian curvature. Curvature of the interior of triangle ABC, plus what you will get is the total geodesic curvature of the edges. That is the total curvature. Okay, and this total is exactly A plus B plus C minus pi. Okay, so it's very, very interesting. And this is a very beautiful thing as to what happens to your simple statement that the sum of the three angles of a triangle is 180 degrees, what happens to it in geometry? And in fact, the truth is, this is true in absolute generality. You take any surface now, okay, you take any surface. The surface need not be a surface of constant curvature, it need not be like a sphere, surface of a sphere, or surface of a pseudosphere, it need not be part of the plane. It can be a varying surface. Now you take a varying surface, again draw a curvilinear triangle and calculate a plus b plus angle a plus angle b plus angle c minus pi, and lo behold, you will exactly get the total curvature. That is the Gauss-Bonnet theorem. It works on any surface, for a triangle on any surface. And I will tell you one more interesting thing. I told you that what is the surface version of the Gauss-Bonnet theorem? That the total, for a closed surface, the total curvature is given by 2 pi times the Euler characteristic. How did you get the Euler characteristic? By making triangulations. And I told you, when you are doing a triangulation on a surface, you are allowed to have curvilinear triangles. Okay? You can now guess that you can get that Gauss-Bonnet theorem on a surface by making a triangulation and applying this Gauss-Bonnet theorem for triangles on a surface. Okay? After all, the whole surface can be, broken into triangles, and the total curvature can be added over each of these triangles. And what happens is that because of orientations, when two triangles have a common edge, the contributions due to the geodesic curvature on that edge will cancel. Okay. So the truth is that this will also, this Gauss-Bonnet theorem for triangles, okay, will also lead to the Gauss-Bonnet theorem for surfaces, and it will link the total curvature with the Euler characteristic of the surface. Okay. So let me write it more generally. Holds for any curvilinear triangle on any surface. So on any surface you draw a curvilinear triangle, then angle A plus angle B plus angle C minus pi will be equal to the total curvature. And the important thing is, when you do total curvature, remember you have to take the Gaussian curvature part, which is contributed by the interior of the triangle, and for the boundaries you have to take the geodesic curvature. Okay. And of course, sum of three angles of a triangle is 180. You can now break a quadrilateral into two triangles and say the sum of the four angles is going to now be whatever it is going to be. It's going to be 2 times, it's going to be 2 pi. Okay. So if it is 3-sided, it is pi. If it's 4-sided, it's 2 pi. Okay. If it's n-sided, it will be n minus 2 pi. So you can write a statement that you take a n-sided curvilinear polygon on a surface and take the sum of the interior angles and take the difference of that with n minus 2 pi, and lo behold, again you will get the total curvature. Okay. So this is what Gauss-Bonnet is. And the interesting thing is that it links the Gauss-Bonnet theorem for surfaces comes down to Gauss-Bonnet theorem for curvilinear polygons, essentially curvilinear triangles, and that is a generalization of the humble statement that sum of three angles of a triangle is 180 degrees on the plane. Okay. So that's what I want you to appreciate. So I think I will stop here. I just want to add one more thing, that just like in the ordinary geometry of triangles, you have the sine law, the cosine law, you have Pythagoras theorem. Okay. Now you have the same kind of theorems are also true for spherical triangles, and we are going to prove that. Okay. And this is what is called a spherical trigonometry. This was very, very important in those days, because the surface of the earth was a sphere, and then people had to make angular measurements, and they had to navigate. Okay. So there were nowadays, of course, you have satellites and you have advanced equipment, but in those days you didn't have that. So spherical geometry, spherical trigonometry was very, very important in those days, and we will study that, okay, in the course. Okay, so I think with this I have kind of more or less ended the introduction. This is a rather long introduction. In fact, there are more things I can say, but then I think it's pretty long already. So from the next class, I will, the next lecture, I will start really getting into, making definitions and trying to prove formulas. Okay, so we will meet again in the next lecture.